addition to Einstein's field equations that describe the gravitational field around a static, spherically symmetrical, non-rotating massive object such as a star or a black hole. It is given by this expression where c is the speed of light, which is set to 1, m is the mass of an object, and g is the gravitational constant. A geodesic is the path a particle or light ray follows in this curved spacetime. A geodesic represents the straightest possible path. This is a geodesic equation that we will be using, where tau is the proper time experienced by a particle. By substituting the Schwarzschild metric into the geodesic equation for each coordinate and using the Christoffel symbols, we can simplify the equations for the spacetime indices. The geodesic equations derived from this metric describe how objects move in the absence of external forces. This force is a pseudo-force arising between spacetime itself is curved, not because of any physical interaction. For example, for the geodesic equation for time t, this introduces gravitational time dilation. It shows us that the passage of time slows down as the particle approaches the Schwarzschild radius, r equals 2gm. This is the event horizon of a black hole. This is key to understanding how clocks behave in strong gravitational fields, such as those near dense objects. For the radial equation, this shows us the travel to and from the origin. For the polar angle theta, this shows us the motion relative to the equatorial plane. For the geodesic equation for the azimuthal angle phi, this shows us the azimuthal component of motion. Now we'll move on to Kepler's law, which emerges from the radial geodesic equation which we have just seen. Here we have rewritten down the radial geodesic equation. Now we'll be using this to derive Kepler's law, as I have just said, for a circular orbit where dr over d tau equals 0. Now the first thing we'll do is take the orbit to lie on the plane, theta equals pi over 2. This means that sine squared pi over 2 is equal to 1. Now it's important to know that dt over d tau is constant with a fixed radius. We do a trick where we move this component to one side and everything else to the other. We now use chain rule to extract this factor of dt over d tau whole squared, remembering that it is a constant. We then go on to set the radial acceleration, radial velocity, and polar angle set to 0, as they are. Now this means that a lot of terms now are equal to 0. We are left with two equal terms, dt over d tau whole squared, which can cancel out. We can divide through by r equals minus 2gm. Now, another thing to note is d phi over d tau is the angle of d phi over dt is the angular velocity, which is also equal to 2 pi over t. We can substitute and rearrange to get the t squared, giving us a lot of t squared is proportional to r cubed. This is Kepler's law. This gives Kepler's law, which states that the square of an orbital period is proportional to the cube of the orbital radius.